A quiet afternoon in San Francisco in the spring of 1906. Electrified streetcars share boulevards with the first automobiles, a hint of coming changes in the new century. Since the California gold rush of 1849, the city has grown steadily, and by 1906, 250,000 people call it home. Then, suddenly, on April 18th, their lives are shattered by a massive earthquake. Nearly 1,000 people are killed and thousands more injured. Fires rage out of control for 4 days. Novelist Jack London is an eyewitness. San Francisco is gone, he writes. All the shrewd contrivances, the cunning adjustments of a 20th century city have been thrown out of gear by 30 seconds twitching of the earth crust. California's governor commissions a scientific investigation. H.F. Reed, a geologist from Johns Hopkins University, arrives shortly after the quake. He finds creek beds, roads, and fences displaced by up to 15 feet for 300 miles down the California coastline. Reed studies measurements made periodically since the gold rush and discovers that distant points on either side of the quake have moved gradually apart over the last 60 years. His guess is that this gradual motion built up stress near a fracture line in the Earth's crust, and then finally snapped. But Reed has no idea why this would happen, nor does anyone else. For most of human history, people turn to religion or myth to explain the mysteries of the earth. In Mali, they believed the world was molded out of clay by the one God. This mask represents earth and sky connected by water. In Iceland, earthquakes were said to be caused by warring gods, until, that is, Christianity arrived in the Middle Ages, and earthquakes and volcanoes became the work of the devil, originating in hell. Beliefs also differed widely about the Earth's age. In 1650, an enterprising cleric in Ireland even tried to calculate the exact moment of creation. By following the chronology of the Bible, Archbishop Ussher declared that the blessed event occurred on October the 23rd, 4004 BC, at precisely 9 a.m., only 6,000 years ago. But increasingly, science has its own say. How could just 6,000 years possibly account for the Earth's natural features or its proliferation of life? As for the origins of earthquakes and volcanoes, they might well lie beneath our feet. But hell seems an unlikely place. And so as the 20th century dawns, scientists have a good idea of what isn't true, but few hard facts about what is. At the turn of the century, the Earth is still a mystery to the scientists who study it. Its age and origins lie at the center of a great controversy. Most scientists of the time believed that the Earth was formed from material torn from the sun. Then, as the Earth cooled, its crust contracted, buckling, cracking, and collapsing. Geologists thought the parts that were left higher became the continents, and the parts that were lower filled with water and became the oceans. Lord Kelvin, the great British physicist, is determined to settle the matter of the Earth's age once and for all by using this theory of a cooling planet.
Kelvin tried to provide a numerical estimate of how long it would have taken the Earth to cool from this red-hot phase down to a temperature where animals could walk around. And he came up with an estimate of around 100 million years.
Lord Kelvin's name is synonymous with science. The now 80-year-old physicist has been at the forefront of scientific discovery in Europe for over 50 years. At the age of 23, he became the youngest professor ever appointed at Glasgow University and devised the absolute temperature scale that still bears his name. But geologists rejected Kelvin's calculations. Huge rock faces made from sediment surely took much more than 100 million years to form.
People were looking at these enormous thicknesses of sediment. They would go out to the beach and see that these things must have been laid down a millimeter at a time or less, and that the amount of sediment increasing in, say, a bay or a river over people's lifetimes was minuscule. The only possible answer to the dichotomy here between huge thicknesses of sediment and very, very small deposition rates was enormous quantities of time. So when Lord Kelvin said definitively that the Earth could only be 98 million years old, what he was doing, in fact, was ignoring hundreds of years of work by geologists. And in fact, even when they protested that his number was based on pure theoretical considerations without any observational tie, he basically said, "I'm Lord Kelvin," and stuck with it that way.
In 1902, in an increasingly confident Chicago, an American geologist prepares a counterattack. T.C. Chamberlain of the University of Chicago, a scientist of great dignity and authority, rejects Kelvin's most basic assumption, that the Earth was hot when it formed.
And he developed what he called the planetesimal hypothesis, which is that the Earth had accreted from small bits of dust, rock, and small planets in the solar system, in the early history of the solar system, that had come together, collapsed under gravitational attraction to form a solid, cold Earth. The other issue that Chamberlain raised was Kelvin's assumption that the only source of heat in the Earth was the original heat from when the Earth first formed. And Chamberlain said, well, maybe, but maybe not. If there were other sources of heat within the Earth besides simply that original heat, then all of Lord Kelvin's calculations would be questionable. They'd be incomplete. He wouldn't be looking at all of the variables.
Another heat source is found. It's one of the great discoveries of science: radioactivity. In London in 1904 at the Royal Institution of Great Britain, a physicist is about to suggest that radioactive minerals exist throughout the Earth's crust. The physicist Ernest Rutherford plans to say that the heat from such radioactivity throws off all of Kelvin's calculations.
Now, as he was about to say this, and that's why physicists love to tell this story, he looked up and saw that Lord Kelvin was sitting in the back of the room. And he said, "Oh, God," he said to himself, "what am I going to do?" And he remembered at the last moment, he said, "Lord Kelvin's estimate for the age of the Earth need no longer be attended now that we have discovered," as Kelvin pointed out, that his estimates were only good if there were no additional source of heat. And there is such an additional source of heat. And having seen Kelvin's eyes snap open as he mentioned the word Kelvin, he saw Kelvin beam from ear to ear as he established that the Earth was old, but that Kelvin had been correct.
But how old is old? Once again, radioactivity provides an answer with a new technique: radiometric dating.
Now, normal background radiation sounds like this. But this rock is a little more interesting. And it's this rock which turned out to be the clock which allowed us to date the Earth.
The rock contains uranium, an element that loses subatomic particles over time. Those losses change uranium into other elements with fewer particles. It's a process known as radioactive decay.
If you leave uranium around for years, it all turns into lead. But it turns into lead a little bit at a time, so you can measure the rate at which it turns into lead. Once you know this rate, which is not hard to figure out physically by watching the process happen in real time, you can go to a rock sample, break it open, and measure the relative amounts of different kinds of lead and uranium in it, and determine from this how long it's been since the rock cooled.
This was a phenomenal discovery. And in the very earliest, most simple attempts at it, it was discovered that, in fact, the Earth had to be an order of magnitude older than previous estimates had argued for. And the average looked like it was about 2.5 billion years at that time.
Ultimately, rocks are found that are 4.5 billion years old. That's 45 times older than Lord Kelvin's Earth. And 750,000 times older than the Earth of Archbishop Usher. In turn-of-the-century Berlin, the mysteries of the Earth begin to intrigue another scientist. His name is Alfred Lothar Wegener. The son of a strict Protestant minister, he forsakes family tradition to become a professor of meteorology. One Christmas, he receives an atlas and begins to study a map of the Atlantic region.
Wegener later told this story himself. He said, "I started looking at it, and it was really odd." He said, "I'd always noticed, like everybody over the age of 12 has noticed, that Africa and South America fit together." He said, "But this map had information from deep down in the Atlantic Ocean, and what it showed is that that match between South America and Africa goes all the way along the continental shelf, all the way down to the foot of Africa. Now, if this is the case," he said, he thought immediately and pointed it out to his office mate, "this isn't just an accident of sea level that these things look alike. These things look alike because they're connected in some way."
Almost as a hobby, Wegener develops a theory that the continents, once connected, drifted apart over time. But he's an experimental meteorologist, not a geologist. So he spends the next 2 years in Greenland, gathering weather data. He also sets a European endurance record for ballooning, and even proposes marriage in a balloon to Elsa Koppen, the daughter of his mentor at Marburg University. But his theory of drifting continents keeps gnawing at him.
Wegener's original idea about continental drift was a momentary intuition. for it to get to be science, you have to make the idea real.
There were particular kinds of fossils found only in certain parts of the world, which Wegener found very puzzling to explain how they got where they were. This one comes from Brazil. See, it's got a long fish-eating skull, a very long swimming body, and legs that look quite like paddles. But the only other place in the world where these animals have been found was in South Africa. And here is a specimen belonging to the very same species which was found in western South Africa. See here, it's got the same long, thin skull, paddle-like limbs and big, thick ribs. How could this be? These two areas are nowadays 5,000 miles apart with the Atlantic Ocean between them. So what could be the explanation as to how they came to be in those two places?
Wegener then learns that certain geological formations occur in very unlikely places. Far above the Arctic Circle, in the frozen islands of Spitsbergen, there are large deposits of coal. But scientists believe that coal is formed in tropical climates. Wegener also discovers that great rock sheets, the result of ancient glaciers, stretch for miles across tropical South Africa.
You can have glaciers in tropical areas if you've got very high alpine-type mountains, but not great extensive ice sheets, and that's what the evidence seemed to show. And so Wegener argued that those continents couldn't have been there when those glaciations occurred and had to have been either further north or further south.
Putting all the clues together, Wegener suggests that the continents were once joined in a massive supercontinent called Pangaea, or All-Earth. The continents must have moved throughout geological time, drifting across the ocean floor. Before Wegener can publish, war breaks out in Europe. As a reserve officer in the German army, he's called up to fight on the Western Front. Injured early in the war, before the worst of the casualties, he continues to work out his theory while his wounds heal. The result is the origin of continents and oceans, his argument for continental drift. Geologists are not impressed.
Many of them said disparagingly this was a theory of the Earth proposed by a weatherman, who moved continents around the way clouds move, but the Earth is this big solid thing. Continents don't just get up and skate around like pats of hot butter on a skillet.
They were able to show that when there was a major earthquake, the Earth just rang like a bell. It pulsated, and long waves traveled around the surface of the Earth for hours and hours after a major earthquake. Now, existing physical theory said that anything that was strong enough or rigid enough to behave that way when there was an earthquake had to be far too strong to allow continents to move round at the surface.
The soft underbelly of Wegener's 1915 theory was the fact that he did not have a force by which to split Pangaea and then propel its pieces across the face of the globe to take up their positions as the modern continents.
Wegener didn't know what made the continents move, and frankly, I don't think he thought that was his problem. He felt that that was something that other people would have to work on.
In 1930, Alfred Wegener leads a new meteorological expedition to Greenland. He's undaunted by the negative reaction to his theory and has updated his book several times, writing in the 1929 edition that the odds of his theory being wrong are 1 in a million. The new expedition is plagued from the start. Bad weather pushes Wegener and his team over a month behind schedule as they rush to establish 3 bases before winter. On September 21st, Wegener sets out to resupply one of the bases. The temperature is minus 60 degrees. The 200-mile journey is planned for 20 days. it takes 40. Most of the supplies are lost in blizzards.
He said to his closest friend, this expedition is now nothing but a matter of life and death. And then the guy who lived for many years afterward and told this story often said, and then he did something that I'd never heard him do before. He talked about how he felt about the world. All I'd ever heard him do was sort of laugh and smoke and do science. And Wegener said, look, it doesn't matter what happens to individuals. He said, science is a social process. It happens on a time scale longer than a single human life. If I die, someone takes my place. You die, someone takes your place. What's important is to get it done.
After a day of rest, Wegener and his Eskimo guide try to return to their own base. They are never heard from again. Alfred Wegener died just after his 50th birthday. His idea of floating continents, still unproven, even ridiculed as a theory without a cause. The origins of earthquakes and volcanoes also remained a mystery. But in the years before World War II, other scientists become intrigued enough with Wegener's theory to take up his quest. For the next 30 years, they struggled to prove Wegener was right and to find the mechanism that could move continents. Only this time, they turn their attention away from the ground below to a place far more mysterious. This is where scientists seek the ultimate answer. The deep ocean floor, as alien as another planet. In the 1930s, geologists used World War I submarines to learn as much as they can about this new frontier. One of the pioneers is Harry Hammond Hess, a young graduate student fresh from Princeton. Hess had spent the late 1920s as a mineral prospector in Africa, even though he had failed his first mineralogy course and was told he had no future in geology. But despite that prediction, Hess eventually joins the Princeton faculty.
Harry was a totally remarkable character, very quiet, little toothbrush moustache, great sense of humor. If you went into his office, you'd see his desk literally piled that high with papers, letters, minutes of this, minutes of that. I was with him one occasion, and he was looking for something of this, and he came across an unopened letter. He said, "Oh, I sent that letter. I should have sent that letter." And he opened it, and it was a letter to another graduate student 3 years earlier, offering him a place. He said, "Oh, I wondered why we never heard from him." This was Harry.
In 1932, Harry Hess joins a renowned Dutch geophysicist, Felix Venning Meines, who was surveying the Caribbean.
Venning Meines had borrowed a World War I surplus submarine from the U.S. Navy for this purpose. Well, these submarines were not the QE-2. They were small, cramped, not very competent things, and dangerous. Something went wrong and the submarine went way below its designed maximum depth. And only drastic action by the captain actually saved their lives.
Hess and Venning Meines can detect minute variations in the mass or density of seafloor crust by measuring the force of gravity with a specially created device. The delicate pendulums are slightly more attracted by denser rocks, rocks exerting a greater gravitational pull. It's so sensitive, it can only be operated in deep, still water, far beneath the turbulent surface of the sea. The measurements reveal something surprising. Large areas along the margins of continents, where the seafloor seems much less dense than expected.
It was as if pieces of the ocean floor were missing, as if the rocks just weren't even there. And this meant that there were forces actively disturbing the crust. And if that were the case, maybe those forces were also moving the crust.
Harry Hess is at Princeton in December 1941, when Pearl Harbor is attacked. An officer in the Naval Reserve, he travels to New York City the next day to report for active duty. By 1943, he's the captain of a transport ship in the Pacific. It's equipped with sounding devices, and Hess uses every opportunity to take depth measurements of the ocean floor.
He ended up the war taking in Marines onto some of those horrific landings on the Western Pacific Islands. Throughout the war, he ran his echo sounder, and he came back with an enormous volume of soundings of the floor of the Pacific. It showed for the first time, very clearly delineated, the deep ocean trenches around the western margin of the Pacific. Very curious features.
Then, in the early 1960s, another piece of the puzzle. Core samples of the ocean floor are taken in the middle of the Atlantic. Analysis of the rock reveals that the Earth's crust gets progressively older on either side of an undersea mountain range called the Mid-Atlantic Ridge.
The Mid-Atlantic Ridge has been known for a long time. It caused a lot of trouble when people were laying telegraph cables in the 19th century, have a big mountain range at the floor of the Atlantic, so people knew that it was there.
Researchers find that the Mid-Atlantic Ridge is not only younger than surrounding ocean floor, but it's made of volcanic material.
The Mid-Atlantic Ridge seems to be a pile of cooled lava on top of a fissure or an opening in the Earth's crust through which hot material is constantly coming up from the Earth's interior.
Hess suggests that the mid-ocean ridge is the site at which the continents are breaking apart. The mid-ocean ridge is formed when molten rock rises from inside the Earth and then pushes the crust apart.
Hess suggests that the reason the ocean floor is young at mid-ocean ridges is that that's where new crust is being created.
And so Hess argued that, in fact, not only was new crust in the oceans formed at the surface, but it traveled along horizontally and then dipped down back into the interior of the Earth again, a process called subduction. And this was the true significance of the ocean trenches, which he'd spent so much of his earlier years working on.
Hess writes this idea up in an article. He calls this paper an essay in geopoetry, because of course he knows that Wegener was severely criticized 30 years before for an idea that was not that different. So by calling it geopoetry, he's taking a kind of moderate stance. Don't get too upset, don't take this too seriously, but I think it's clear that he believes the theory is true.
Hess's theory suggests that the sea floor moves due to circulating currents deep inside the Earth. The material beneath the crust is kept hot by the constant decay of radioactive elements, causing convection currents that move the ocean floor along. New crust is created at mid-ocean ridges and destroyed at deep ocean trenches, Hess suggests. A never-ending conveyor belt. moving at a snail's pace through the ages. His paper is greeted skeptically by the geological community. But at Cambridge University in 1963, geophysicists Fred Vine and Drummond Matthews uncovered new evidence that supports Hess's theory, evidence based on rock magnetism.
They, with a brilliant piece of lateral thinking, looked at the ocean floor south of Iceland, but in other places as well. And south of Iceland, you've got part of the mid-ocean ridge in the Atlantic. And there was a feature of the ridge which had been known for a long time, but no one had understood. And that was that there were curious magnetic stripes on the ocean floor parallel to the ridge crest.
Throughout geological history, there had been times when the Earth's magnetic field had reversed, meaning the North Pole had become the South Pole and the South Pole had become the North Pole. Since rocks are like little magnets, they would point in the direction of the prevailing magnetic field. And then, as the crust split apart, if there had been a magnetic reversal in the meanwhile, this next set of rocks would point in the opposite direction.
And they were able to show that the width of these magnetic stripes was proportional to the known durations of these normal and reversed epochs in geological history. Furthermore, the stripes were generally symmetrical on either side of the ocean ridge, as Harry Hess's seafloor spreading idea would have suggested.
It's nuclear testing during the Cold War that provides the clinching evidence. In an effort to monitor the tests of other countries, the United States and Britain set up a worldwide network of seismometers, which also detect earthquakes. Now, geologists can map the locations of earthquakes with unprecedented accuracy. And soon, a pattern emerges with stunning clarity.
The earthquakes occur in exceedingly narrow bands, and these red spots are shallow earthquakes, and you can see them following the crest of the mid-Atlantic ridge all the way down. If we look over here in the Pacific, you can see that these necklaces of oceanic islands and the deep ocean trenches that lie against them are associated with earthquakes too.
You put this all together, and what you get is plate tectonics. The idea that the Earth's crust can be broken up into large pieces or plates that consist of both continents and also pieces of oceanic crust moving together over the face of the Earth.
The movement of the plates is only a few centimeters a year. But that's enough to reshape the Earth, build mountains, trigger earthquakes, and create volcanoes. Volcanoes erupt where the crust splits apart or where it subducts, and molten rock is forced up from below. Mountains, like the Himalayas, form where plates carrying continents collide, crumpling up the land over millions of years. And earthquakes occur along the boundaries of tectonic plates, like the San Andreas Fault. In 1906, the Earth had suddenly snapped along the fault line, releasing pressure that had been building up for years, caused by the slow, steady movement of the tectonic plates. Our planet is not merely a static platform for life. Although it appears placid from outer space, the Earth is dynamic, violent, unpredictable, constantly reshaping itself, much as Alfred Wegener had suggested 50 years earlier. Alfred Wegener wasn't the only scientist in the early 20th century whose work remained controversial for years. Charles Darwin's theory of evolution was still being fiercely debated decades after his death in 1882. Where Wegener conceived a new theory about the evolution of the continents, Darwin offered one about the evolution of life itself. Many of Darwin's contemporaries denounced his notion that all living things evolved from simpler, more primitive forms of life over millions or billions of years. Most of the Western world believed instead in the biblical idea of creation over 6 days. At first, Darwin didn't deal specifically with human origins, except to say that light will be thrown on the origin of man and his history. Then, in 1871, he published The Descent of Man, leaving no doubt that he thought that man, too, had descended from more primitive animals. Darwin expected the book to be denounced, but even he would have been surprised by the depth of prejudice among scientists long after his death, a prejudice that would shape the study of human origins through much of the 20th century. In 1900, we know precious little about our prehistoric ancestors. Our best clues are in their ancient bones. But even these are few and far between. Only one bone in a billion hardens into a fossil to await discovery through the millennia. The fossils that turn-of-the-century scientists have to work with were all uncovered in Europe and Asia. In Germany's Neander Valley, human fossils were found in 1856. The ancient ancestor who provided them was dubbed Neanderthal and was thought to have lived a few 100,000 years ago. 12 years later, this skull was found, estimated to be 20 to 30,000 years old. It was named for the cave in France where it was discovered, Cro-Magnon. And in 1891, Java man was found by a Dutch anatomist in Indonesia and dated at 500,000 years or more. But was any of these fossils the human-like ancestor who first evolved from the apes on the road to modern man? In 1909, some amateur scientists believe they have found the answer. In Sussex, England, near Piltdown Common, in a gravel pit beside a farm road, a worker's pickaxe hits what looks like a coconut shell. Solicitor and part-time geologist Charles Dawson examines the fragments and decides they are parts of a human skull. By the summer of 1912, Dawson and a small team spent weekends digging for more fossils. One day, they find 3 pieces of a human skull and an ape-like jawbone with 2 teeth that look human. They share the evidence with Arthur Keith, a distinguished anatomist who was determined to trace the ancient origins of the British. Dawson believes the skull held a brain as large as modern man and is the oldest human fossil ever found. He dubs it Dawson's Dawn Man. Sussex celebrates its native son.
It was an instant hit. It really resonated with all of the thinking about how we became human. And it was immediately embraced by the English anthropological community.
These people believed that the brain, being so critical in humanity's survival and adjustment to life must have been enlarged early on in human evolution, while the teeth and the posture must have caught up later.
The Piltdown discovery was very Eurocentric. Not only was he the first Englishman, but he was older than anything that had been found in Europe. Not only did the brain have preeminence, but the English had preeminence.
The Crown knights Arthur Keith and 2 others for their work on Piltdown. And Britain is proud to be seen as the birthplace of modern man. But in 1924, the preeminence of the British is threatened by a surprise coming out of Africa.
There was a lime works called the Buxton Lime Works, about 130 kilometers north of Kimberley, where the diamonds came from. And there was a contaminated lime, pinkish, not pure white lime. But the pink material had in it bones.
A lime worker named De Brain had been collecting baboon skulls for some years. One day, he notices a strange skull and sends it off to anatomist and new dean of the medical school in Johannesburg, Professor Raymond Dart. On November 28, 1924, Dart's closest friend is about to be married in Dart's garden. Dart is the best man. As he's dressing, a curious crate arrives at his house. Inside it, he finds chunks of limestone and the fossil of a brain.
First thing he noticed was this endocast. This is the infillings of the brain case that reflect some of the convolutions and some of the blood vessels in the side of the brain. And because Dart was so carefully schooled in brain anatomy, as he had studied in England, he recognized that this could not be some kind of a monkey.
A thrill of excitement shot through me. It was no ordinary anthropoidal brain, Dart writes later. Most people would have dismissed the fossil as a chimpanzee, but Dart is sure he's onto something.
Dart was already something of a heretic in science. And I think it appealed to something in his makeup that he was going to overturn some of the fixed ideas of the time. One of the fixed ideas was that the discovery was in the wrong continent.
There was this view that everything important that happened in human history had to have happened in Europe. White European males thought that we must have evolved in Europe. How could we have come out of Africa? Look at how primitive Africa is.
And it was considered to be the most unlikely scenario for human origins to look at this great so-called dark continent of Africa.
The box holds another surprise. A tiny skull embedded in the rock. No diamond cutter ever worked more lovingly or with such care on a priceless jewel, he writes.
4 weeks later, when the skull face came out of the rock and he could look at the teeth, to his amazement, he saw that the canine tooth, the eye tooth, was small, like that of a human, not enlarged and fang-like, like that of a chimpanzee or gorilla. And here is the lovely little face. of the child, with its small canine. We have a full house of deciduous teeth, baby teeth, still busy erupting.
And he was able to fit in the brain case or the endocast so that you had a little child's skull. It was a remarkable moment of revelation for him.
Dart declares, "I knew at a glance that what lay in my hands was the replica of a brain 3 times as large as that of a baboon." But then Dart, the anatomist, notices something unexpected.
The base of the skull pointed to the head being poised on an upright spine, not hanging forward on an oblique spine, as one finds in creatures that go on all fours instead of on 2 legs.
It possessed that single important hallmark that it was walking upright.
Dart was suggesting, in a word, that this creature was knocking on the door of humanity, but hadn't quite crossed the threshold yet. A staggering thing. It was the very personification of a missing link. A link between animals, non-human animals, and humans.
And I think probably trickling through his mind was that statement made by Charles Darwin in the late 1800s when he predicted that Africa would prove to be the cradle of humankind.
Dart names the fossil the Tong skull, after the district where it was found. After he writes up his findings, he ships them off to England, to the distinguished journal Nature. But the editor is skeptical. Because infant apes look more like humans than their parents do, it's easy to make a mistake.
They felt that Dart had not proven the case, nor that he could prove the case on a child. Give us an adult, and we might listen to your case.
Most see no need to upset the status quo.
People said, we have Piltdown. We already have a fossil that's maybe 1 million years old, and it's very modern looking, it's very advanced.
Piltdown Man upholds British pride and racial stereotypes as well. Dart's find threatens all of this. The British are adamant that Piltdown, not Tong, is the missing link. Although Dart continues to believe he's right, he admits it's no good being in front if you're going to be lonely. While scientists wrangle over whether humans originated in Europe or Africa, with big brains or small, others are outraged by the idea that humans descended from apes at all.
Dateline, Dayton, Tennessee, July 11th, 1925. Charles Darwin's theory that all mankind had descended from a common ancestor had set off the fireworks. John T. Scopes, a Dayton biology teacher, had decided to test a new Tennessee law that forbade the teaching of any theory that denied the divine creation of man. He was arrested and indicted. A full house of avid spectators from all over the nation filed in to hear the debate. The issue was no longer the innocence or guilt of Scopes, but rather the death struggle between 2 basic human philosophies, fundamentalism versus modernism.
Scopes is found guilty and loses his job. But no one believes the public debate will end here. The scientific debate also continues to rage. It's not whether humans evolved from apes,